No, that's coordinate.
حد سمعني أصلا؟
Yeah.
عاملين إيه؟
تمام. شو اخبارك انت؟
يلا.
Okay. When share screen. Share screen. Okay. This is screen. جماعة شايفين؟
شايفين.
Okay. تمام. في assumptionين بس we took them يعني إنه في chapter 10. The first assumption اللي هو creeping flow. Yeah, طبعا chapter 10 all is talking about approximate solutions for the Navier-Stokes equation. Okay. The approximate solutions for the Navier-Stokes equations are يعني you don't solve it exactly. So in chapter 9 we solve it exactly. Of course يعني not for any type of flow, but for a certain boundary condition that you are given. Then we cancel the terms that are not in our problem. But then we solve it exactly, okay, using differential equations. Mainly we solved ones يعني that have ordinary differential equation, but you can also solve ones with partial differential equations, like I think in the last example, okay, there was the diffusion equation where you solve this term, I guess, partial u by partial t equal to mu partial u squared, partial squared by partial whatever that u depends on. يعني maybe the u depends on the z direction or maybe in the y direction حسب يعني الارrangement بتاع الفلو. We can also solve this one. This is the diffusion equation and you took an analytical. Here you have second derivative, here you have first derivative. You need one boundary condition for the time and you need two boundary conditions for this one, and then you can solve it. Okay, but يعني we didn't went through يعني partial differential equations. نشوف السؤال بيكون طويل. ولكن in this chapter we do approximate solutions. يعني these terms might not cancel, but what will happen to them is that we cancel them using the order of magnitude analysis. Okay, this term is مثلا of order of magnitude of 10 to the power 4, and that term is order of magnitude 1, so that one is clearly smaller than that, something like this. Okay, so now we have a drop of water. This is the first assumption, which is the creeping flow. And also it's called Stokes flow, I guess, Stokes flow. And also it is low Reynolds number flow. Okay, so what happens in low Reynolds number flow? In low Reynolds number flow, you see the dimensionless form of the Navier-Stokes equation, where it is something like this, I guess. The dimensionless form 1 over Reynolds number, yes. And this is the viscous terms. Viscous terms اللي كانوا هم عبارة عن Laplacian squared over of V, okay, star, okay. And when Reynolds number is very low, يعني let's say that it approaches 0. Now this term, okay, will approach infinity. It is very large compared with other terms, okay, اللي هم inertial terms. So يعني viscous terms are dominant with respect to the inertial. So you cancel the inertial terms, okay, اللي هم first parts في Navier-Stokes equation. But then equal to, the only part that will be left for you is the pressure terms here. You have the pressure terms, which is Euler number, I guess. P star, I don't remember it actually, but it is initiated with, or associated with Euler number. Okay, also the gravitational terms will be cancelled because they are inertial terms. Or you cannot maybe cancel them. Let's see, according حسب السؤال. Now in this question, okay, let us look at it. We have a drop of water in rain that has a diameter of 42.5 micrometer. The air temperature is 25 Celsius and its pressure is standard atmospheric pressure. يعني the air temperature 25 Celsius والpressure is equal to 1 atm. How fast does the air have to move vertically so that the drop will remain suspended in the air? فيعني معناها we want this drop of rain to be suspended in the air. Okay, يعني معناها we have force balance here. Okay, what type of forces we have? Okay, you will learn مثلا في عندنا أول شيء gravitational force وفي عندنا drag force. في عندنا البايونسي فورس كمان upward. So F buoyancy plus F drag should be equal to the gravitational force. Okay, I know how to calculate the gravitational force and the buoyancy force, but how to calculate the drag force? مشكلة الدراج فورس أو يعني إنه الفلو. Let's talk about flow. The flow have مثلا two characteristic or two properties, important properties for each flow. You have rho, you have a mu. Okay, and material properties for that flow or properties of that flow. لاحظ إنه in Bernoulli's equation we don't observe اللي هي mu. Okay, we don't see mu. Okay, I think this question in Dr. Scammel first quiz, the one in the review, محمد صح انت اخذت TSD. He says يعني انه why we don't see mu in the Bernoulli's equation. And Bernoulli's equation assumes inviscid flow. Okay, Bernoulli's equation, one of the assumptions for Bernoulli's equation is inviscid flow. And for inviscid flow, okay, the inertial forces are dominant, are much higher than the viscous forces. So that's why you don't see the mu. Okay, you only see rho, V, these things. Okay, pressure term come on. But now, okay, now let us just assume that this flow, okay, to know how to calculate the drag, let us just assume that this flow is highly viscous. Okay, so now you will not see rho in the equation, okay, of the drag force, of course. The drag force of a creeping flow is not a function of its density. It is a constant multiplied by mu, multiplied by V, multiplied by the characteristic length, which is in this case the diameter. Okay. This is the drag force equation for creeping flow. Why it is not a function of density? Because the viscous forces are more dominant. Okay, so let's use this equation for now. Okay, the drag force for low Reynolds number flow, and then after we finish and after we calculate what is the velocity, and velocity هي المجهول في equation, then we will return back and calculate Reynolds number. So this is something similar to what you did in internal flow. Okay, remember in internal flow, you first assume, let me assume that it is laminar, and then after you get the velocity, you calculate Reynolds number. So يعني same thing, same principle. واضح؟ Okay. Let us now assume that it is an inviscid flow. Okay, so sorry, it is a creeping flow, and now we know this constant for ball cross section. Okay, for a ball, this constant will be 3 pi. Okay, for a ball it is 3 pi. Let's do the force balance. Yeah, one buoyancy force, I guess it will be very small in air. Buoyancy in air is very small, so I guess you can ignore it. There was a question in the slides in which you did the same thing, but the difference is that the particle was moving with respect to the air. This is the air, the particle is moving. Now here, the particle is suspended and the air is moving. There is no difference. يعني في النهاية velocity that is here in this equation, in the drag equation, which is 3 pi mu VL VD. The V is the relative velocity between the object and the medium. So if the air is moving and the ball is fixed, or if the ball is moving and the air is fixed, still it is the relative velocity between them. So nothing will change. يعني that he changed in this problem, we need to calculate the velocity of the air. Okay, so يعني keep this in mind. There is nothing different here. You will use the relative velocity. Both of them are moving. Of course, you need to see what is the relative velocity between them. Okay. Now here we have plus. Okay. The equal to the gravitational force. This is a ball, of course. So what is its mass? Okay, mass multiplied by g. Okay, and plus the equation of the buoyancy force was rho v d. صح? Or VD, if I remember. Okay, just let me check the buoyancy force equation because I forgot it. Buoyancy force. Yeah, it should be. Yeah. Rho multiplied by G multiplied by, what is this? Rho G T square pi over 6. O multiplied by the volume multiplied by G, not D. Oh, sorry. Okay, so rho VG, because it's a force. Okay, rho VG. Okay, rho of the fluid. Here we have the velocity. Okay, yes. So now we need to calculate the velocity, okay, of that flow, and that's it. What is the velocity of that flow, which is here? V here, V here. Substitute everything that we know. We know the G, okay. And what is the mass of the ball? The mass of the ball, we are not given it directly, but you are given the rho of the ball, I guess, okay, because it's a drop of rain. So we can know the density of the ball. And we know the volume of the ball. What is the volume of the ball? It is 4 over 3 pi r cubed. So this is the volume of a ball. Equal to, here, 3 pi, the mu of what? Okay, mu of this flow. Okay, so because we have external flow, so mu of air, okay, not mu of the ball, of course, and we are interested in the flow, and V, which is the relative velocity, and D, okay, which is the diameter of the ball, plus, again, here we have rho of the fluid, okay, for the buoyancy force. What is the rho of the fluid? We can get it, of course, and the volume, okay, the volume of the submerged part of that particle. مثلا, this is, let's say this is water, this is a rock that is sinking. For the rock that is sinking, we need now to, when we calculate the buoyancy force for this rock, what we say is that the buoyancy force, okay, the volume in the buoyancy force is the volume that is displaced. So because it is all submerged in air, then all of the volume is displaced. So this is the volume of the ball again. And this is the gravitational acceleration, okay? Let's just substitute. Let me get the values, okay, for them. Here's the values. Okay. I'll write them down here. So we have minus rho pi, okay. Rho of air is equal to rho of air is rho of air. Okay, it is 1.184. This is raw air. And raw water, okay, which is the particle, is equal to, I found it, this 998. Of course, at that temperature, you have tables for these things. Okay, kilograms per meters cubed. Kilograms per meters cubed. And we also need mu of air, which is equal to 1.849 multiplied by 10 to the power minus 5. And these are all the properties that we need. Yes, 2 rows and 1 mu. So let me get back. The diameter of the ball is, diameter of the ball, yes, 42.5 micrometer. So let's substitute, substitute with me. 998, okay, 998 multiplied by pi over 3 pi, okay, 4 over 3 pi r squared. This is the diameter, so we put 42.42.5 divided by 2, which is 21.25, and because it is micrometer, so multiplied by 10 to the power minus 6. Okay, here it is cubed plus 3 pi multiplied by mu of the air, which is 1.849 multiplied by 10 to the power minus 5, then multiplied by the velocity, which is unknown, and then multiplied by the diameter, which is 42.5, multiplied by 10 to the power minus 6, because it's micrometer, equal to the mass. Again, the mass is rho V, okay, so rho of the water again, 998, multiplied by pi over 3, 4 over 3, pi 21.25 multiplied by 10 to the power minus 6, all of it cubed, and then multiplied by 9.81. Okay, then multiplied by 9.81. Sorry, 9.81. Rho of, this one is rho of the fluid. Okay. So rho of the fluid, which is 1.184. Yes. Yes, and that's it. Let me substitute it, 1.184 times 4 over 3 times pi times 21.25 times 10 to the power minus 6, okay, to the power 3. And again multiplied by 9.81. So this one is, I think this term, which I called here buoyancy force, turns out to be 4.669 times 10 to the power minus 13 newtons. So we can ignore it. I think in the solution manual the book ignored it, but for the slides the professor accounted for it. So I just accounted for it to make you best just think or remember, there is buoyancy force, but it is very small, so we can ignore it. Okay, and this is the gravitational force. Let me calculate it. For the gravitational force, just change the mu, okay, or the gravity force, multiplied. Okay, so this one is 9.81 times 10 to the power 3, 10 to the power minus 6, 21. Okay, and then yes. So this one is the same thing, just multiplied by 1,000. Okay, and the difference in the density from air to the water is 1,000. And this 3.9 35 times 10 to the power minus 10. Okay, it is a very small number as well, but it is much larger than this one. And it is approximately 1000 ضعف منها. Okay, we can ignore this term with respect to this term. وآخر شيء we have اللي هو this term, which is 3 multiplied by 3 multiplied by pi multiplied by mu, which is 1.849 times 10 to the power minus 6, multiplied by the velocity, which is unknown, and then multiplied by d, which is 42.5 times 10 to the power minus 6. Okay, it is 7.4 times 10 to the power minus 10 velocity. Okay, just now let's calculate the velocity. 4.669 times 10 to the power minus 13 plus 7.4 times 10 to the power minus 10 x should equal to 3.935 times 10 to the power minus 10. Now we'll get the velocity, which is 0.5311, okay, meters per second. Let me ignore this term and show you what will the velocity become. Okay, so if we ignore the buoyancy force, I will get a velocity of 0.5318 تقريبا, which is let's calculate the percentage error. تقريبا it is 0.13% error. Okay, so you can ignore it, because but it's not always ignore the buoyancy force, but ignore buoyancy force when the particle is suspended in air, because air is have a very low density. That's it. Okay, enough of this. Let us focus on our question. Now, what is left? What's left is again calculate Reynolds number to verify that this flow is creeping flow. So let's calculate Reynolds number using the velocity that we calculated. Reynolds number is rho VL over mu, which is rho 1.184 multiplied by the velocity, multiplied by L. L is the characteristic length يعني. So now because this is an external flow across a ball, so the characteristic length will be D. Okay, so D is 42.5 times 10 to the power minus 6 over mu, which is 1.849 times 10 to the power what? Times 10 to the power minus 6. Okay, let us just verify for Reynolds number يعني to check. Or not verify, check يعني. And because if Reynolds number is high, then our solution is wrong, and we need to use the drag force formula that does not assume inviscid flow. Sorry, that does not assume creeping flow. That one contains density in it. Okay. 1.184. What was the density? 1.184, 0.0. The velocity is 0.0. The velocity is 0.053. Okay, so 0.0. What is the 0 again? There. Okay. So 0.053. Okay, and then density. Okay, here the viscosity is -2 to the power -5. So now Reynolds number is 0.1445. Okay, which is تقريبا يعني close to 0. It is much less than 1. Okay, for balls, I guess when you have, it is a rule of thumb, if you have Reynolds number very less than 1, then you can say, this is creeping flow. Okay, and it is obviously a very small number. It is 0.1445. So, okay. السؤال ما فيه شيء اصلا you will not solve Navier-Stokes equation because now Navier-Stokes equation for this flow عبارة عن pressure terms, okay, pressure terms equal to the viscous to the viscosity terms. If you put it like this, okay, what we have V, okay, and here we have pressure, okay, the pressure gradient, okay, طبعا هيكون positive لأنه طلع الطرف الثاني, okay, the pressure gradient. So yeah, this is a differential equation, okay. Here second order, here first order, we can solve it of course, but it is done already for us, and we know now the coefficient for the drag force, okay, which is 3 pi for a ball. You can do, I think, experiment Professor Khaled told you about, and know the coefficient for each for different type of flows across different bodies. مثلا you drop مثلا cube مثلا, and then you drop مثلا any other shape, so you will know this coefficient, okay, because now the drag force is only a function of mu, v, and the characteristic length. Okay, هذه سؤال ما فيه شيء المفروض انه يكون سهل. بس إذا عندكم اي سؤال قولوا لي. Now the second one.
لا بقول لك كلير.
مش سامع.
بقول لك كلير.
اوكي. Okay. The second approximation or second assumption is the inviscid, okay, assumption. هو that بالعكس. Now the inertial forces are very dominant, and the viscous forces are the smaller ones. So now, okay, viscosity terms will be gone, or viscous terms will be gone in the Navier-Stokes equation, and we will end up with Euler equation. Okay, Euler equation from fluid mechanics. You just have the material derivative, okay, material derivative of the velocity. Okay, I think this is how the material derivative was. Then equal to, okay, the gradient of the pressure, and then plus the gravitational force. That's it, Euler equation. Plus 0. The viscosity forces are not there. Okay, so this is Euler equation. So when we have viscid flow, you can use also Bernoulli's equation, and Bernoulli's equation is the solution of this equation, okay, for the pressure. Okay, and Bernoulli's equation, you can. I think there is a problem where you need to find Bernoulli's equation from the Navier-Stokes equation. Okay, and you find it from the Navier-Stokes equation. We've done it before. We've done one, yes, in chapter 9, before we took assumptions, where we did flow over the tornado one. Remember it? Okay, the flow was rotational. And I told you then we will use this assumption. طبعا لما يكون flow rotational, okay, that's the important thing. Rotational. Okay, this means that it is inviscid. Okay, so every irrotational flow is inviscid, but sometimes we can have inviscid flow, okay, when the flow is rotational. Okay, and an example for that is fluid moving as a rigid body, okay, or rigid body rotation. And where we have مثلا a cup and there is water here مثلا, and we put مثلا a fan, something, okay, and or a spoon, and we are ejectating the water, okay, we are making a circular motion, okay, or it is rotating with a certain omega, and the flow is moving as a rigid body. So in this case, yes, the flow is rotational, but it is inviscid. But every irrotational flow is definitely inviscid. Okay, so the first thing to know if the flow is rotational or no is to compute the curl. Okay, compute the curl of the flow, and if the curl is equal to 0, then the flow is irrotational, meaning that it is inviscid. Okay, so that's how we know that the flow is inviscid, and that's also why it calls the rotational assumption. Okay. So the problem, okay, that we have here, now we need to consider a steady two-dimensional incompressible irrotational velocity field. خلاص, irrotational velocity field معناها this velocity field is inviscid, and for inviscid flow we have an equation, okay, or something called the velocity potential that is defined for inviscid flows. Okay, and the equation for the velocity potential, okay, this is it. Okay, so now we can compute for each one of the velocity components. And we don't need the Navier-Stokes equation just for the pressure computation, as I told you. Okay, because all the velocity components can be calculated from the velocity potential. Okay, relation here. The gradient of the velocity potential is equal to 0. And we also can get from the velocity potential we can get اللي هو individual velocity components U, V, or W, and also we can get the stream function, okay, which is here part of the question. So yes, let's continue in the inviscid, okay, inviscid approximation or irrotational approximation. Now we have صح كمان في شيء there is a question I think about also a rotating flow like that in part 2 in the slides, okay, but that one we didn't use the velocity potential because the flow is rotational, and the flow is rotational, but it was rigid body rotation, okay, or rigid body rotation, and for rigid body rotation the flow is rotational, okay, and it is inviscid at the same time, but we cannot use the velocity potential because the velocity potential is only defined for irrotational flow. That's why I think it's better to call it the irrotational assumption. Okay, the irrotational, يمكن also the book calls it the irrotational assumption. And as a result from the irrotational assumption, we have the property of the fluid that it is inviscid, okay, or of our flow. But it is preferable because we had a question in part 2 where the flow is rotational, okay, and it is inviscid at the same time. But now we cannot use the velocity potential because it is clearly rotational. Okay, it is rotating in rigid body rotation. So you use the Navier-Stokes equation, okay, to compute the pressure. Yeah, and I think you had information about the velocity components because the flow is rotating and he tells you what is UR and what is U theta, this stuff. But now the question is in reverse. I have the velocity potential, I want to calculate these components, okay, and the flow is rotational. Okay, the flow is rotational. So because the flow is rotational, is also implicit as a result, and I can use the velocity potential because it is rotational, and this is the velocity potential. Okay, this is its equation. Calculate the velocity components u and v from this velocity potential. طيب what is the u and what is the v؟ متذكرين الجدول اللي قلت لكم عليه في how to get the components from the steam function. There is also a similar schedule, but how to get the velocity components for from the velocity potential. Okay, let me minimize and show you that one. Okay, going to Teams, drop it, then share again, share my desktop. This is the book. Okay, this is the book. Okay. Not this. Yes. Can you see it? Okay. This is similar schedule to the اصلا حتى يعني بيختصر عليك لانه في كمان فيه الستريم فانكشن معه. So from now on يعني don't look at that one with the stream function only. Look at this one. It have the velocity potential and it have the stream function. So either if you have the velocity potential, I can get the u component, or if I have the stream function, I can get the u component. Okay, and also I can get the v component, and also I can get the z component from the velocity potential. Okay, because the velocity potential is defined yani, for 3D flow, not like the stream function. Okay. Yes. So now let us go. Okay, it is just saying the derivative with respect to x, the derivative with respect to y, the derivative with respect to z بالنسبة للvelocity potential. Stream function لو عارفين the derivative with respect to y and minus the derivative with respect to x to get the v component. Okay, so let's now get the both components. What is the v component? It is the derivative of the velocity potential with respect to y, and the derivative with respect to y is minus 3y. صح؟ بعدين صح 2 بتنزل تحت فهتكون minus 6y. Minus 6y plus 4x and then minus 5. Okay, so this is the v component, and the u component is the derivative of phi with respect to x, which is equal to 6x squared, 6x plus 4y, and then minus 2, and this is the u component. So we found the first thing. We calculate the velocity components. Then verify that the velocity field is irrotational. How is that? How can we verify that the velocity field is irrotational? We do the curl, the curl of that flow. And if the curl is 0, then the velocity component is irrotational. So how can we do the curl? Curl of the velocity is equal to, put here your matrix ijk, because it's a cross product, ijk, and here you have partial by partial x, partial by partial y, partial by partial z. Okay, here we have u, v, and z. Okay, and this, okay, is of course equal to 0. Okay, so and we will not use this one because the flow is two-dimensional, so we can only use this. Okay, and directly also we know it. Okay, k, it is in the k direction. Okay, because if you put a cross product between the v and the u and the v, then what's the resulting direction? In the k, so, and this is in the i and this is in the j. But that row is equal to 0, and you don't have مثلا لو تتذكروا how can we find the determinant of a matrix? Okay, so you multiply this by this minus this by this, okay, then multiply by that upper one, صح? And then again مثلا if you hide this مثلا you multiply this by this minus this by this, okay, and then multiply by I, صح? And then this by this multiply by this by this, then you get that one. Okay, so now because the flow is two-dimensional, we only have these two components. So multiply this by this by this, and it will be in the k direction because the flow is two-dimensional only. So what is the partial by partial x of v minus partial by partial y of u. This one should be equal to 0 in order to be irrotational, in order for the flow to be irrotational. Okay, so let us do it. What is the derivative? طبعا الماتريس تختلف بتاعت المultiplication. Okay, بتاعت الفايندينج اللي هي الكيرل if the flow is cylindrical. Okay, I don't remember يعني مش I don't remember, I didn't took even يعني هو إنه cylindrical coordinates. Okay, analytical. So for you, I guess because you took it, so you are required also to do or to know how can you do a cross product in cylindrical coordinates. Okay, I think it is related to the ER and EU and E theta, or EZ, let's call it, and some of the unit vectors have derivatives with respect to the direction. So I guess partial ER by partial theta and partial E theta by partial theta, something like that. I don't remember both those two or something else, but they have derivatives. But for the unit, for the Cartesian unit vectors, they don't have derivatives with respect to the direction. Okay, so that's the difference here. It is somehow different. I guess you can find it on the internet. So if you put curve matrix in cylindrical coordinates for the cross product يعني. Yes, this is it. Okay, and now here it's done, I think, for the electric field. It's the same thing, just take the electric field and put the velocity. So it is 1 over r, okay, and here theta, and here k over r, okay, because some of the unit vectors do have derivatives, okay, in this direction. Okay, but the kernel matrix in Cartesian coordinates, the unit vectors do not have any derivatives. Okay, so yeah, it's just like that. No x, no I, j, k. That's it. Okay, in Cartesian coordinates. In cylindrical coordinates, there is some manipulations, and also here we have r, here we have r sign. Okay, and also in the spherical coordinates it will be different. Okay, but you can do it, yani, of course, and you do it the mathematical way, yani, without the matrix, and you expand it. Okay, this minus this minus this. Okay, I do it in detail. Okay, what we wanted to do. Oh yes, so let us derive partial v by partial x. So what is v? Minus 6y plus 4x minus 5. The derivative with respect to x is 4. Minus, what is the derivative of u with respect to y? It is also 4. So 4 minus 4 is equal to 0. This flow is clearly irrotational. Okay, this irrotational. Now part 3, you have to generate an expression for the stream function in this region. Easy. Now we have the u and the v. This is a question from chapter 9. How can we generate an expression for the stream function? You say that partial the stream function by partial y is equal to u. Okay, and then the stream function is equal to, okay, integrate u with respect to y. So what is the integration of u with respect to y? It is 6y squared, okay, or 6y squared over 2 minus 2y plus 6y. Okay, صح. Okay, let me write it like this: 6y minus 2y, then plus what term we had here? 4y. Okay, so it is 4y squared divided by 2. 4 divided by 2 will be 2. And here we have y squared. Okay, this is the plus a constant, okay, or a function of that depends plus a constant. Let me write it now as a constant. As a constant, okay. And now you derive this one, okay. So you derive it. It will be 6, I guess, partial psi by partial. Okay, but this constant you should define what is this with respect to what. because this velocity potential depends on both x and y. Okay, we integrate with respect to y. And the crony يا جماعة. We integrate with respect to y, so this function is a function of x. Okay, remember, don't forget. So now partial psi by partial x, the negative is equal to v, which is equal to, derive with respect to x now. You have 6y, you have this is 0, everything else is 0, plus the derivative of this function, okay, which is equal to the v component. Where is the v component? This is it. Minus 6y plus 4x minus 5. So minus 6y plus 4x plus 5. Plus 5 or minus 5? Minus 5. Okay, so this, okay, the those two should be equal, okay, which are 6y plus the function of x. Okay, you can take 6y to the other side, so you'll have 12 minus 12y plus 4x minus 5, and then f of x is equal to 12 minus 12yx plus 2x squared minus 5x. Okay, now you know this function of x, plug it here, and there you have it. You have the stream function for your flow. Okay, you can also do it in the reversed way. At first, partial psi by partial x negative equal to v, calculate the psi plus a function of y, and then get the function of y later on. Okay, this is very easy in this approximation and nothing else. You have, just you need to know how to calculate the curl, okay, or cross product. Okay, and then after you know how to calculate the curl, everything is easy. And let me go with you for the slide question. Okay, which one was this one? This one. And this one was the same. Even ولكن the flow is a polar flow with 2D cylindrical flow. And this question, okay, this question, well, professor get it from examples. The flow is in rigid body rotation, as I told you, so you cannot use the velocity potential, and even he doesn't want you to calculate the velocity components. He is giving you the velocity components. He wants from you to calculate the pressure. Okay, so you go to Navier Stokes equation, okay, or Euler's equation for now, because the viscous terms are not there. Okay, even though it is rotational flow, but it is in rigid body rotation. So in rigid body rotation, the flow is inviscid. Okay, you go. This is Euler's equation. Substitute your velocity components there. Okay, which is r the u. Okay, u z u r u theta. Okay, your velocity components. This is the curl of the flow. To know that the flow is rotational, and this is the curl of the flow in cylindrical coordinates. Now you know that the flow is rotational. Okay, 2 omega ez. Okay, and then after you substitute your velocity components there, now you calculate the gradient of the pressure. Okay, what is the gradient of the pressure there? And then it will be a differential equation, ordinary differential equation, first order. Calculate now the pressure, and you have boundary conditions. Okay, so you can calculate this function of z. That's it, yeah. And then he asks you to find the constant of Bernoulli's equation. This it will be. If the flow is okay, very important. If the flow is rotational, okay, rotational, like this case, rotational, but it is inviscid, then Bernoulli's constant, okay, will not be constant everywhere. It is only constant across a streamline. Okay, so across a streamline, that's why we said that in Bernoulli's equation is constant across a streamline, because the C will define, مثلا this C, this is C1 مثلا, this is C2, and this is C3. For each constant C, you will have Bernoulli's equation applicable. But if you have a rotational flow, then C is constant everywhere. So this flow, this streamline, and this streamline, this streamline, this streamline, this streamline, all have the same C. Okay, so we can say, and all the slides say that a rotational flow is more restrictive, okay, than the inviscid flow. Okay. What else? Oh, okay, let me continue. Okay. And that's it. You have another one, I guess, where the flow is in the book, where the flow is now the curl is 0. Yes. So the constant is constant everywhere. I think this one. I think the curl is 0 if you did for the velocity flow. I'm not sure, but if you calculate the curl, just check it. If you do the curl for this cylindrical flow, then you will know whether your velocity is rotational, okay, or whether your flow is rotational or rotational. And if it is rotational, then your C is constant everywhere, and you can use the velocity potential function, okay, or a definition. That's it. These are the two approximations that you took so far. They are, I guess, easy. They are not like the boundary layer, okay? Where in the boundary layer, what you do, okay, delete. Yes, maybe next tutorial we will solve more examples, but now using the Navier-Stokes equation to calculate the pressure. Okay, but for now these two examples will be enough. But for the boundary layer, just to get you an introduction, the boundary layer, okay, let's say that this is a bar, okay, or anything, a plate, okay, and we have here flow, external flow, okay. Now here, this region, okay, where the flow is like developing in this case, you have like that, okay. This is called the boundary layer, okay, the boundary layer, okay. And in this boundary layer, or inside the boundary layer, the viscous forces, okay, are dominant. And here outside of it, okay, and here outside, you can use Euler equation. Okay, because the viscous forces, we assume that they are very small. But inside the boundary layer, the viscous forces cannot be ignored. Okay, so 1 over Reynolds number, okay, 1 over Reynolds number, it is a high number. Okay, so Reynolds number, it is a very small one. So that's why we need to consider the viscous flow on this side here, and outside you can get away without computing the viscous force. Okay, and usually it is defined at the region where we have the velocity here, okay, is equal to 99%. Okay, 99% of the free stream velocity, which is here. So 99% of the free stream velocity. This is very good, to enclose the boundary layer here. And outside of the boundary layer, where we have that the flow is uniform, تقريبا, it is not affected by this plate. Okay, so this is the boundary layer approximation. It includes many things. And I feel in my opinion, it is the hardest part in the chapter. Okay, but hopefully you can get through it. You understand and solve problems. So yeah, that was it for today. عندكم أي سؤال, أي question, anything?
كله clear. يعطيك العافية.
Okay. مش مشكلة بالنسبة لبارت البريشر. We will solve more problems إذا ما فهمتوا آخر part. We will solve ممكن 1, 2, 3, I don't know. Then we will continue with boundary layers. تمام. Yes. تمام. السلام عليكم.
السلام.